Hey team, Dr. Jack Order here, and in this video I'm going to be taking you through the electron microscope. I've been showing you so many beautiful electron microscope images throughout my videos. I felt it was so important that you understand how it works, why we use it, and what are its benefits. So let's jump into it here. First of all, the electron microscope. Why did we invent it, right? What problem were they trying to solve when they invented it in the 1930s? They were trying to solve a major shortcoming of light microscopy. So to understand electron microscopy, we have to understand this shortcoming in light microscopy. So I'm going to be using a lot of heuristics, which again are an oversimplified model that help you understand what's going on, even though they may not be 100% accurate, because what we're about to talk about, a lot of it turns into quantum physics, which is, we're not going to go into quantum physics, okay? So we're going to go through heuristics, which are simple models to understand this world. So the first thing is light travels in waves, right? Light is a wave in the electromagnetic spectrum, and the wavelength dictates what color it is. So smaller wavelengths are blue, longer wavelengths are red. Now, when our eye sees these wavelengths, it gets converted into white light in our brain. So white light isn't actually a physical phenomenon, it's a neurological phenomenon essentially. That's kind of buzzy. That's hard to comprehend. Anyway, the important thing is light travels in waves. So how does traditional vision work? How does the traditional microscope work? Well, a lot of it works by the absorption of light, and that generates either colors or darkness. So here's an object that we want to see, and here's a sensor. That sensor could be our eye, or it could be an electronic sensor. So here's an object that we want to see. We send light at it, wavelengths come along, they hit it, they're either absorbed or scattered away perhaps. And so then we end up with part of our sensor not detecting any light, and so that would be a shadow on our eye, for example. And so we would now see this as a dark blob and these as light. So it would be a dark circle in a light space. And that is how we see, that's how microscopes work, that's how light works, right? But what if we want to look at something really small? What happens when we see those wavelengths go past? They barely interact with it, if they do at all, right? Because a big wave is going to struggle to interact with something small. Just imagine sitting in the bath, and you make a tiny little ripple and it heads towards you and it hits your belly. And then you look behind you, you're not going to see a ripple out the other side. You've completely blocked that ripple, which is a wave. You've completely blocked that. Now imagine floating up to your shoulders in cisterns in Tasmania or Chopu or Jaws or any of these other big wave destinations. Portugal, there's some big ones in Portugal, right? So any of those big waves destinations, you see a wave coming at you and it's 6 meters, it's 10 meters, it's humongous. You can't stop that wave. In fact, that wave is barely going to interact with you and it's just going to wash over you. You can't block any of it, right? That's a good heuristic, a good analogy for what's going on here. There is a limit to how small a thing we can see with visible light because of the wavelength of visible light. So wavelength, visible light, it's sort of 400 to 750 nanometers in the electromagnetic spectrum. There are other things in the electromagnetic spectrum, like radio waves, which are bigger, and X-rays and gamma rays, which are smaller. So you might say, why don't we just use one of those really, really tiny waves like X-rays or gamma rays? Now, you can probably already guess why. They don't really interact with physical things very well at all. That's why we use X-rays to look through our body. It so weakly interacts with tissue that it travels straight through our muscle. How are we supposed to see a cell if it doesn't interact with the cell? It's just going to go straight through the cell that we're trying to see under the microscope. Gamma rays go straight through us, and they even go through a good chunk of lead before they are stopped. So it's because they're weakly interacting. So basically, when we want to look at something incredibly tiny, the electromagnetic spectrum isn't the right thing to use. So what should we use then? I would like to mention, just to really highlight the point, this is not to scale. So let's have a look to scale. Let's zoom in on a coronavirus next to a blue wavelength. Here's our coronavirus. Here's the blue wavelength. This is the magnitude of the problem we're trying to deal with here. let me zoom out just so we can see that to scale there. This is what we're talking about, right? You can clearly see that there's nothing this little virus could do in a coherent way to interacting with this electromagnetic wave here to cast a shadow or provide really any information at all, right? So this is the problem. So where did we go? Well, they went to electrons. Now, we're all familiar with electrons as, you know, the source of electricity, but also those circulating particles around a nucleus. So they are negatively charged particles that travel around a nucleus. Now, these electrons are fortunately also waves. This is particle wave duality. But what's the wavelength of an electron? This depends a little bit on things like voltage, but on a typical electron microscope, the wavelength is around 0.01 nanometers. So if I was to put that to scale next to this coronavirus, it's thinner than this line, okay? So now wavelength is not the problem when it comes to resolution of the electron microscope. They can see down to phenomenal levels. So how does it work? Well, let's first look at a light microscope, just a quick refresher, and then jump into an electron microscope. So a light microscope, we focus the light with a lens called a condenser. It hits the cell, for example, that then is scattered out to a lens. The lens then redirects the light back into our eye, and part of it might cast a shadow like the nucleus there. And so we would see the nucleus from casting a shadow. So now let's look at an electron microscope. It's set up very similarly. We shoot an electron beam. Oh, sorry, there's the shadow. I wonder where that was going to pop up. That's the shadow of the nucleus there. So now let's look at the electron microscope. We shoot an electron beam at it. We focus that electron beam. That then interacts and is scattered, or it's either scattered or it goes straight through the sample that's incredibly thin. We cut the sample incredibly thin. It is then focused by another lens. Now you might go, wait on a minute, lenses don't work with electrons, and that's 100% true, but electrons can be manipulated by the electromagnetic spectrum. They're charged, so we can warp them with magnets. Now we don't use naturally occurring rare earth magnets like that. We use electromagnets. So these just manipulate the they're basically magnets that can manipulate the path of the electrons, right? So if the electrons are flying out, they can redirect the magnets back in. Pretty much in the same way that the electron is attracted to the proton. It's because of that electromagnetism. That's then picked up by a sensor, and again we can get a shadow cast because perhaps some parts of the cells are better at scattering those electrons, and other parts of the cells are better at letting those electrons go straight through. And so it's essentially working exactly like a light microscope. And this is the key point here. It works exactly like a light microscope, but instead of lenses, it's got electromagnets, and because the electron has such a small wavelength, we can detect smaller things like viruses. Now this we call transmission electron microscopy because the electron beam is going through the tissue. So it's called transmission electron microscopy. Now there's another kind of electron microscopy called scanning electron microscopy, and it's very similar to another kind of light microscopy. This is called a dissection light microscope, and instead of light coming through the tissue, which would be very difficult if you were dissecting something or doing surgery on something, for example, because light can't get through tissue very well, instead the light comes from the top. It then hits it and is scattered and redirected up into the microscope, focused via lenses, and then viewed. Now the scanning electron microscope works exactly in the same way. So we've got our sample here, this time we've got our sensor on the side, an electron beam comes down and again is being focused by electromagnets. The electrons are then scattered off the tissue, and that scattering is then picked up by a sensor which also focuses the electrons again with an electron magnet. And this scanning electron microscopy is where we get these absolute beautiful surfaces. It doesn't have to be a thin section anymore like a transmission electron microscope. We can actually pick up surfaces. Now what we do sometimes, because perhaps the surface that we're trying to look at isn't very good at scattering electrons. So instead of scattering the electrons just go straight through it. So sometimes we coat the sample in a heavy metal like gold. So we use really fine gold particles, really fine gold. We coat it in really fine gold. Gold, being really heavy and dense, is excellent at scattering the electrons. So now we can see it. So sometimes we have to coat it in gold. So this is just some pollen, and pollen is amazing and has so many peculiar shapes under the electron microscope. So it's a beautiful thing to see. And this is transmission electron microscope, so we can see what the viral particle is blocking out. And here's another beautiful scanning electron microscope image of a eye of a fly. So this is actually, when you think about it, quite a macro image. So you can actually view relatively big things under the electron microscope, particularly the scanning electron microscope. Right, so that's scanning electron microscopy. I hope you enjoyed it. Yeah, stay tuned, like and subscribe. Thanks, guys.